Hello, my friend. Tonight, we'll take a quiet journey together to the very edge of the universe. This isn't a lecture or a race to learn. It's a gentle unfolding of cosmic ideas, explained slowly and clearly, so you can drift into sleep while still feeling that sense of wonder. If you're new here, know that these videos are made to calm your mind, ease your thoughts, and carry you off to rest under the stars. Let's begin. Chapter 1. How do we define the edge of the universe? When people ask about the edge of the universe, it is natural to imagine a wall at the end of space, a place a spacecraft could reach and touch. That picture is intuitive, but it is not how modern cosmology treats the question. In general relativity, space and time fuse into a smooth space-time that bends and stretches according to well-tested equations. In this language, an edge would be a boundary of space-time itself, a point where the mathematical description fails. The universe we observe shows no sign of such a border. Instead, the limits we confront arise from causality, the finite speed of light, and the history of cosmic expansion. The observational boundary is the most immediate. Because light travels at a finite speed, we see only as far as light has had time to reach us since the universe became transparent to photons. All points whose light has arrived by now form the observable universe. Its center is not special. Every observer sits at the center of their own observable sphere. Although the universe is about 13.8 billion years old, the present-day radius of the observable universe is roughly 46 billion light-years, because space expanded while the light was en route. Everything we study directly with photons lies within this sphere, not because space ends there, but because signals from farther away have not yet had time to arrive. The same expansion that makes the observable universe so large explains why a hard spatial edge is unlikely. On the largest scales, the cosmos is well described by homogeneous isotropic solutions to Einstein's equations. Galaxies are not fragments from an explosion into emptiness. They are nearly at rest with respect to the large-scale flow and are carried apart because the scale factor, the parameter that measures the size of space, increases with cosmic time. Distances grow because the metric, the mathematical rule that turns coordinates into measured lengths, changes. In such a picture, there is no preferred center and no surrounding void into which the universe expands. There is therefore no obvious place where the stuff runs out. How far back we can look is set by the thermal history of the early universe. For hundreds of thousands of years, the cosmos was a hot plasma of electrons, protons, and photons that scattered incessantly, preventing light from traveling freely. Around 380,000 years after the start of the hot early phase, electrons and protons combined to form neutral hydrogen, drastically reducing scattering. From that moment, the universe became transparent, and the oldest light has streamed ever since. We observe that relic radiation today as the cosmic microwave background, a nearly uniform glow with tiny temperature variations that record the early distribution of matter and energy. It is not a wall but a surface of last scattering, the most distant curtain that light can cross. To make edges precise, cosmologists use horizons. The particle horizon is the greatest comoving distance from which light could have reached us since the start of the hot phase. It encloses the region that has ever been in causal contact with our world line and marks the ultimate reach of information about the past. The event horizon looks forward. Given the future expansion driven by dark energy, It is the boundary separating regions from which light emitted now can and cannot ever reach us. In our best fit models, its present-day proper distance is on the order of tens of billions of light years, about 16 billion given typical parameters. A third scale, often confused with a true horizon, is the Hubble radius, the distance at which recession speed equals the speed of light at a given time. Objects can move from inside to outside the Hubble radius and still be seen, so it is not a causal boundary. None of these horizons is a material wall. They are boundaries set by causality and by the expansion history. If we ask instead whether space itself has a border, an absolute place where space ends, the standard answer is no. General relativity allows spatial sections that are infinite in extent, in which case there is no edge to find. It also allows spaces that are finite yet unbounded. The classic analogy is the two-dimensional surface of a sphere. The area is finite, but there is no rim to fall off. A three-dimensional version of that idea would be a universe that is finite but without boundary. Locally, such spaces can look flat if their overall size is very large compared with the region we inhabit. Observations place tight constraints on geometry and possible closure. Measurements of the cosmic microwave background, the large-scale distribution of galaxies, and the baryon acoustic scale collectively indicate that spatial curvature on the largest observable scales is extremely small, consistent with zero within current uncertainties. This near flatness does not prove the universe is infinite. A sufficiently large finite space can look flat within our small region. Cosmologists have also searched the microwave background for signatures of a compact topology, such as matched circles that would appear if light had wrapped around a finite universe and reached us along different paths. No convincing pattern has turned up, which pushes any potential closure far beyond our observable patch. A different boundary concerns time rather than space. The name Big Bang can mislead if we imagine an explosion from a point into emptiness. In modern cosmology, the Big Bang is shorthand for the very early, hot, dense state of the entire universe. Classical theorems in general relativity show that, under broad conditions, cosmological spacetimes are geodesically incomplete to the past. Past-directed world lines cannot be extended indefinitely. Many models of inflation, a brief episode of extremely rapid expansion, are also past incomplete. What, if anything, lies beyond that boundary requires a quantum theory of gravity we do not yet have. Proposals range from a bounce from a prior contraction to scenarios in which time itself emerges from deeper degrees of freedom. Relativity also furnishes horizons tied to particular regions. A black hole's event horizon is the boundary of a region from which nothing can escape to the distant universe. It is not a solid membrane, and a freely falling observer crosses it without noticing anything singular locally, yet globally it marks a definitive limit to communication. These examples teach the broader lesson that edges in relativistic physics are causal boundaries, not places where the manifold ends. Cosmological horizons belong to the same family. The balloon analogy is often used to visualize expansion. Dots painted on the surface of an inflating balloon move apart as the surface stretches, and there is no preferred center within the surface. The analogy helps because it emphasizes that distances increase as the surface itself expands, not because the dots slide across it. But it can mislead if we imagine the balloon embedded in an external three-dimensional space and go searching for the edge of the rubber. In the real evidence of a surrounding space into which our three-dimensional space expands. For the two-dimensional beings living on the balloon, the surface is all there is. For us, the same is true of our three-dimensional space. Distance in cosmology comes in several flavors. Proper distance is the instantaneous separation between two co-moving points measured along a spatial slice at a given cosmic time. Co-moving distance factors out the overall expansion, so galaxies at rest with respect to the cosmic flow keep fixed coordinates. Light travel distance is the photon's flight time times the speed of light, which differs from the proper distance to the source when the photon arrives because the intervening space has stretched. Using the right definition avoids apparent paradoxes about edges where none exist. Causality also clarifies what can ever be influenced. We routinely observe light from galaxies whose present recession speeds exceed the speed of light. There is no conflict with relativity because recession speed is not motion through space. It arises from the expansion of space itself. Photons emitted when those galaxies were closer can surf the changing geometry toward us even while the galaxies continue to recede. By contrast, a galaxy that is now beyond the cosmological event horizon is forever outside our future light cone. No signal we send today will ever reach it. Inflation, if it occurred, offers a straightforward reason why we may never encounter a spatial rim. In many models, a small patch that was once causally connected is stretched to such enormous size that our entire observable universe occupies a minuscule portion of it. The mechanism explains the uniformity of the microwave background, the near-flat geometry, and the pattern of primordial fluctuations that seeded galaxies. Some speculative versions of inflation even suggest a multiverse, a vast mosaic of regions with differing local conditions. Whether or not that picture is realized in nature, the conservative implication is already striking. Beyond what we see, there is likely more of the same. Not a wall. With these pieces in place, we can answer the question carefully. If by edge we mean a spatial border where space ends, our best supported models provide none within or even remotely near the observable universe. Space may be infinite or it may be finite but unbounded, closing on itself at scales so large that current data cannot reveal the closure. If by edge we mean a limit to what we can see or influence, cosmology supplies quantitative boundaries, a particle horizon that demarcates the region ever in causal contact with us, and a future event horizon beyond which signals sent now will never arrive. The absence of a rim to the cosmos can feel disorienting because our senses were tuned for rooms and shorelines. Yet the scientific picture is more satisfying than a cliff at the end of everything. It provides a clear, testable way to discuss what can be known and what cannot, and it has already explained why the sky is uniform on the largest scales, why galaxies cluster as they do, and why some regions will slip forever beyond contact. If there is an edge worth contemplating, it is the moving horizon where evidence meets curiosity. New instruments continually push our observational limits outward. Infrared telescopes peer through dust to catch the first galaxies. Precision surveys map subtle patterns in the microwave background, and radio arrays will trace the neutral hydrogen of the cosmic dawn. Each advance widens what counts as within reach, even though the underlying causal horizons remain. And if we allow a brief reflection, it is this: living in a universe without a wall means there may be no balcony outside the story from which to view it whole. We carry our light with us. Each step forward does not shrink mystery. It enlarges the circle of illumination, and the dark beyond retreats, not because it ends, but because we have learned how to see a little farther. Chapter 2. The Observable Universe, Our Cosmic Bubble. The phrase observable universe carries a precise meaning in cosmology, yet it can sound deceptively simple. At first hearing, one might assume it is merely the part of the universe that human technology has mapped with telescopes. In truth, it is a boundary dictated by the most fundamental principles of physics: the finite speed of light, the age of the cosmos, and the geometry of space-time. It is not an arbitrary limit set by our instruments, nor is it a material barrier waiting in the distance. It is the natural horizon created by causality itself. The observable universe is a sphere centered on the observer. Its radius is determined by the maximum distance from which light has had time to reach us since the moment the universe became transparent to radiation. For us, that distance is about 46 billion light-years in every direction. This is much larger than the age of the universe in years, because while light was making its way toward us, the fabric of space expanded, stretching the paths those photons traveled. The fact that the observable radius exceeds the naive estimate of 13 or 14 billion light-years is a vivid reminder that cosmology requires a framework beyond common intuition. This cosmic sphere is not fixed. At any given moment, every observer, no matter where they are in the cosmos, has their own observable universe. A galaxy that lies at the edge of our horizon today also has its own horizon, centered on itself. There is no universal center. Instead, there are countless overlapping bubbles, each defined by the point of view of a particular observer. The image that emerges is of a cosmos where the concept of an edge is always personal and never absolute. What fills this observable sphere is both astonishing and humbling. Billions upon billions of galaxies lie within it, each containing hundreds of billions of stars and likely even larger numbers of planets. Yet what we see is not a snapshot of these objects as they exist today, but as they were when their light began its journey. A galaxy whose light has traveled 10 billion years shows us an ancient version of itself, one that may look nothing like its present form. The observable universe is not simply a volume of space. It is a time machine filled with fossils of cosmic history, showing us the deep past stretched across distance. At the farthest reaches of the observable universe lies the cosmic microwave background, the radiation released when the universe was only about 380,000 years old. Beyond that surface, photons could not travel freely because the universe was opaque. That glow is a curtain of sorts, the limit of what electromagnetic radiation allows us to perceive. But within the observable sphere, we can trace a remarkable story. Nearer than the microwave background, we find the first stars igniting after hundreds of millions of years of darkness, the birth of galaxies, and the gradual structuring of the cosmic web. Closer still, we witness galaxies colliding and merging, clusters forming, and the scaffolding of dark matter pulling luminous matter into the filaments we observe today. The geometry of the observable universe is described by the framework of general relativity, where space-time can expand. Galaxies do not travel through space in the way a rocket crosses the sky. Instead, the space between them stretches, carrying them apart. This stretching creates redshift, the lengthening of the wavelength of light as it journeys through expanding space-time. The farther a galaxy, the greater its redshift, and the more ancient the era we are witnessing. Through careful measurements of these redshifts, astronomers reconstruct the expansion history of the cosmos and its contents. Understanding the observable universe also demands grappling with different measures of distance. Proper distance, comoving distance, luminosity distance, and angular diameter distance are not interchangeable. They answer different questions: how far apart 2 points are now, how their positions evolve with expansion, how bright something appears, or how large it looks. For nearby objects, these measures converge, but on cosmological scales they diverge, reminding us that space is not static. Distinguishing among them ensures clarity in how we describe the observable bubble and the objects within it. Though vast, the observable universe is not the whole universe. Nothing in our current knowledge suggests that space stops beyond the horizon. If anything, inflationary theory predicts that the universe beyond our sight is far larger, potentially infinite. What we call observable is merely the portion of the whole that has had time to communicate with us. The rest, hidden beyond our horizon, is no less real. It continues to evolve in parallel, governed by the same physical laws, though perhaps with variations in structure or detail we cannot verify. One of the most striking implications of the observable boundary is its individuality. If intelligent beings live in a galaxy 30 billion light-years from us, their observable universe overlaps with ours, but is not identical. They would see galaxies and structures invisible to us, while some of what we see would remain forever beyond their reach. No single observer can ever see the entire universe. Each is confined to their own causally defined bubble. This relativity of perspective is not a limitation of our tools, but a deep truth of the cosmos itself. The observable universe also evolves with time. As the universe ages, light from more distant regions has time to arrive, expanding our observable horizon. The observable universe of today is larger than it was 1 billion years ago, and smaller than it will be 1 billion years hence. Yet there is a countervailing effect, the acceleration of cosmic expansion due to dark energy. While light from more regions continues to arrive, many galaxies are being carried away faster than light by the expansion of space, and eventually they will cross our event horizon. Those galaxies are still visible now, but the light they emit in the far future will never reach us. This dynamic interplay between what we can see now and what we will lose to cosmic acceleration ensures that the observable universe is not just a static bubble, but a shifting boundary changing with cosmic time. Another key insight comes from the fact that the observable universe is finite in information content. The number of photons in the microwave background, the density fluctuations imprinted upon them, and the galaxies mapped across the sky are a finite data set. We may refine our measurements, build larger telescopes, and capture fainter signals, but the total number of distinct pieces of observable information is not infinite. This is one reason why cosmology, unlike laboratory physics, cannot endlessly repeat experiments under new conditions. The observable universe offers a single grand experiment, one history, one set of signals to interpret as best we can. The idea of a cosmic bubble also forces us to rethink what it means to live at the center. For centuries, humanity resisted the idea of not being central, first displaced from the center of Earth, then the solar system, then the galaxy. Yet in the observable universe, every observer is again at the center of their own horizon. This does not restore the old hierarchy because the symmetry is universal. All locations enjoy the same privilege. Being at the center of our observable bubble is not a mark of cosmic importance, but simply the geometry of causality. There are, however, limits to what we will ever know about the regions beyond our horizon. No matter how advanced technology becomes, no signal emitted now from galaxies beyond the event horizon can ever reach us. For those regions, their histories are sealed off from ours. This creates a permanent boundary to empirical knowledge, a line between what can be tested and what can only be hypothesized. Inflation and other theories give us reasons to think the universe is far larger, but confirmation will never come from direct observation. The observable universe is thus both a triumph of knowledge and a reminder of its limits. Astronomers nonetheless exploit every available window within the observable sphere. Infrared telescopes pierce dust and capture the glow of the first galaxies. Radio arrays trace the faint hydrogen signals from cosmic dawn. Future instruments may detect gravitational waves from the earliest epochs, giving us glimpses even closer to the beginning. Each advance expands the richness of our observable data, even if it cannot change the fundamental horizon. The observable universe is not static. Our ability to study it grows as ingenuity builds new ways of listening to the cosmos. It is worth noting that the observable universe is not smooth. On small scales, it is filled with complexity. Stars, planets, dust, magnetic fields, black holes, and all the structures born of cosmic evolution. On the largest scales, it reveals patterns. Clusters of galaxies strung along filaments, vast cosmic voids spanning hundreds of millions of light years, and the overall homogeneity that arises when we zoom out far enough. This hierarchy of structures is itself evidence for the physics of the early universe, encoded in the spectrum of density fluctuations seeded during inflation and amplified by gravity over billions of years. The cosmic microwave background, the ultimate boundary of our vision, is not uniform. Its tiny variations in temperature map the seeds from which all later structure grew. Studying those fluctuations has allowed cosmologists to infer the universe's age, contents, and geometry with remarkable precision. In that sense, the outermost surface of the observable universe is not just a limit, but a treasure trove of information, the canvas upon which the early universe left its signature. As profound as these scientific insights are, the concept of the observable universe also carries philosophical weight. It reminds us that reality is larger than any horizon, that what we can know is always shaped by where and when we live. It forces us to accept that ultimate knowledge may be bounded, not by failure of imagination, but by the nature of space-time itself. And yet, far from diminishing our place, this realization expands it. To know that we live inside a bubble defined by light's journey is to recognize that we are bound to the universe by threads of causality stretching back nearly to its origin. Every photon that reaches us carries a story of where it came from, and together those stories weave the history of the cosmos. Our bubble is not a prison but a record, and to read it is to discover that we are not apart from the universe, but inseparably within it. For just a moment of reflection, one might say, living inside such a bubble means that we will never see the whole, and yet within our limited horizon lies an immensity beyond measure. To exist here is to inhabit both a limit and a gift, the boundary of what light allows and the vastness of everything it reveals. Chapter 3. The Expanding Fabric of Space. When we look at the night sky, what we see is not static. The galaxies scattered across the heavens are in motion, carried away from one another by the steady stretching of space-time itself. This expansion of the universe is one of the central discoveries of 20th century astronomy, and it remains the key to understanding nearly every feature of cosmology. The idea that space itself can expand is profoundly different from ordinary notions of movement, and clarifying it helps us distinguish between a universe with an edge and one that is endlessly unfolding without borders. The first hints of expansion arose in the early 20th century when astronomers began measuring the spectra of distant galaxies. Vesto's slipper was among the first to notice that light from many spiral nebula, what we now know as galaxies, was shifted to longer wavelengths. At first, these redshifts were a curiosity, but when Edwin Hubble compared them with distances derived from Cepheid variable stars, a remarkable pattern emerged. The farther away a galaxy lay, the greater its redshift. This became known as Hubble's law, and it suggested that the entire cosmos was stretching. The discovery dovetailed with predictions from Einstein's theory of general relativity. Solutions to the field equations found by Alexander Friedmann and Georges Lemaitre in the 1920s showed that a universe filled with matter and radiation could not remain static. It must expand or contract. Einstein had initially resisted this implication, introducing the cosmological constant to hold the universe in balance, but Hubble's observations confirmed that expansion was real. From then on, the picture of an evolving, dynamic cosmos became unavoidable. Expansion is not like an explosion. In an explosion, fragments of debris move through space into an external void, with the explosion center marking a privileged point. In cosmic expansion, there is no central point. Galaxies are not flying outward into emptiness. Rather, the space between them is stretching. Every region of the universe expands in the same way, so that no observer sees themselves at a special location. The pattern of redshifts arises because photons traveling through expanding space have their wavelengths stretched, just as the distances between galaxies are stretched. To visualize this, cosmologists often use analogies. One is the surface of a balloon being inflated. Galaxies are like dots painted on the surface. As the balloon grows, every dot recedes from every other dot, even though none is moving across the surface itself. The analogy works well in showing that expansion is uniform and centerless, yet it can also mislead. The balloon expands into a surrounding three-dimensional space, while in reality, our universe is not expanding into anything we can point to. The expansion is intrinsic. Distances grow because the metric of space-time itself evolves. Another analogy is raising bread dough. As the dough rises, raisins move farther apart, though none of them moves independently. Again, the dough does not expand into a void. It expands within itself. A crucial feature of expansion is that it is governed by the contents of the universe. Matter, radiation, and dark energy each influence how the scale factor evolves. In the early universe, radiation dominated and expansion was extremely rapid. Later, matter took over, slowing expansion as gravity pulled on structures. In the current epoch, dark energy, with its repulsive effect, drives acceleration. These transitions shape the large-scale structure we see today. Without expansion, galaxies would never have drifted far enough apart to allow the universe to cool. Without acceleration, distant galaxies would not be slipping irreversibly beyond our horizon. Understanding the expansion also clarifies why distant galaxies can appear to recede faster than light. Hubble's law relates recession velocity to distance, and for galaxies far enough away, that speed exceeds the speed of light. At first glance, this seems to contradict relativity. But relativity forbids objects from moving faster than light through space, not from being carried apart by the expansion of space itself. No galaxy outruns a beam of light locally. Instead, the photon's path is stretched along with the fabric of space. In fact, we routinely detect photons emitted by galaxies that were receding faster than light when the photons were released, because expansion slowed enough along the way to let the light make progress toward us. The redshift of galaxies provides a window into expansion history. Each photon's wavelength is stretched by the factor of expansion that has occurred while it traveled. By measuring the redshifts of many galaxies and comparing them with their distances, astronomers reconstruct how the universe has expanded over time. The pattern reveals a cosmos that slowed in the past, when matter dominated, and then began to accelerate a few billion years ago under the influence of dark energy. Observations of Type 1a supernovae in the 1990s provided the first strong evidence for this acceleration, transforming cosmology and pointing to the mysterious component that now makes up about 70% of the cosmic energy budget. The expansion of space is also responsible for the cosmic horizon described in the previous chapter. Because light travels for a finite time while distances stretch, there is always a limit to how far we can see. The observable universe is therefore not a simple snapshot of a static stage, but a consequence of expansion carrying regions beyond our reach. Moreover, the event horizon created by accelerated expansion means that many galaxies we see today will eventually vanish from view, their light forever unable to catch us as expansion outruns their signals. While we often talk about expansion on the scale of the entire universe, it does not affect everything equally. Bound systems such as galaxies, solar systems, or atoms do not expand with the cosmos. Gravity, electromagnetism, and the nuclear forces hold them together against the gentle stretching of space. Expansion matters only on scales where the average density of matter is too low to resist. Thus, galaxies move apart while stars within galaxies remain bound. The Earth is not growing farther from the Sun because of cosmic expansion. Its orbit is dictated by local gravity. The fact that expansion is selective underscores its nature as a large-scale phenomenon rather than a universal stretching of all distances. Cosmic microwave background radiation gives the clearest evidence for the expansion's history. The tiny temperature fluctuations across the sky match predictions of a universe that has expanded and cooled for nearly 14 billion years. Those fluctuations also record the sound waves in the early plasma, whose wavelengths were stretched by expansion. The positions of the peaks in the microwave background's power spectrum provide precise measures of the universe's geometry, composition, and rate of expansion. Without the framework of an expanding cosmos, the microwave background would be impossible to interpret. Another consequence of expansion is the concept of moving coordinates. To describe galaxies being carried apart by space, cosmologists use a coordinate system where moving positions remain fixed for objects at rest with the expansion. In this language, the scale factor tracks the growth of the universe, and physical distances are simply moving distances multiplied by the scale factor. This convention highlights that galaxies are not moving across coordinates, but are instead nearly stationary while the metric stretches. The discovery that expansion is accelerating raises profound questions about the fate of the universe. If dark energy remains constant, galaxies will continue to recede until only the nearest cluster remains visible to us. Over trillions of years, even that cluster may fragment under expansion. Stars will die, galaxies will fade, and the universe will head toward a state of isolation and cold emptiness. This heat death is not imminent on human timescales, but it is the natural outcome of a cosmos whose fabric stretches faster and faster. If dark energy changes with time, other outcomes are possible, from slower expansion to catastrophic rip-apart scenarios. In every case, the fate of the cosmos is tied to the behavior of its expanding fabric. Inflation, the theorized episode of exponential expansion in the universe's first tiny fraction of a second, highlights the power of this idea. In less than a trillionth of a second, inflation could have stretched a microscopic patch into a region vastly larger than our observable universe. This solves puzzles such as why the universe is so uniform across vast distances, why it is nearly flat, and why there are no unwanted relics from early physics. Though inflation ended long ago, it shows that expansion is not a passive background effect, but an engine capable of reshaping the cosmos. Evidence for inflation remains indirect, seen in the pattern of fluctuations in the microwave background, but many cosmologists view it as a compelling explanation. The expanding fabric of space also influences our perception of cosmic time. In everyday life, distances and intervals are fixed, but in cosmology, what counts as now across distant regions depends on the expansion history. Light from a quasar billions of light years away shows us a time when the universe was young, yet that light arrives in our present. The linkage of space, time, and expansion forces us to accept that the universe's story is layered across distance and perspective. Every photon we detect has been stretched by the expansion, turning the cosmos into a record of its own history. The expansion of space also ties together the smallest and largest scales. Quantum fluctuations during inflation, stretched to cosmic sizes, became the seeds of galaxies and clusters. Without expansion, such tiny irregularities would never have grown into the web of structures we see. The fact that microscopic randomness can be magnified to sculpt the large-scale universe is one of the most remarkable consequences of expansion, uniting the physics of the quantum with the destiny of the cosmos. In teaching and popular writing, there's a temptation to picture expansion as something foreign or unnatural. Yet in physics, it is the default. A static universe would be more puzzling, requiring finely tuned conditions to prevent either collapse or runaway growth. Expansion is the natural behavior of a universe filled with energy and governed by relativity. It is only our everyday experience of a mostly static Earth and solar system that makes expansion seem strange. As with many cosmological concepts, the expanding fabric of space invites both humility and wonder. We know that every galaxy we see is riding this vast current, carried outward not by motion but by the geometry of spacetime itself. The distances are immense, the timescales almost beyond imagination, and yet the mathematics describing it is precise, tested, and predictive. Observations confirm again and again that the fabric of space is stretching and that its expansion holds the key to both our cosmic past and our eventual fate. If one allows a quiet moment of reflection, the lesson is as much philosophical as scientific. To live in an expanding universe is to recognize that change is not the exception but the rule, that even the emptiness between galaxies is dynamic, alive with stretching motion. Our lives are brief sparks within that flow, yet we are capable of understanding it, of grasping the invisible current that carries all things. The fabric of space expands, and with it, the circle of what we know. Chapter 4. The Cosmic Horizon, Where Observation Ends. Every observer in the universe lives inside a sphere of possibility, a boundary defined not by walls of matter or energy, but by the laws of causality. This is the cosmic horizon, the ultimate frontier between what can ever be seen or influenced and what will remain permanently hidden. Unlike the surface of a planet or the rim of an island, this horizon is not a place that can be reached, crossed, or touched. It is a feature of space-time itself, an invisible limit woven into the structure of the cosmos. Understanding this horizon is essential for cosmology because it dictates what we can measure, what we can theorize, and what we must accept as forever unknowable. The cosmic horizon emerges from the finite speed of light combined with the finite age of the universe. Light, the fastest signal possible, still takes time to cross space. Since the hot early universe began around 13.8 billion years ago, light has only had that long to travel toward us. Yet because space has expanded during the journey, the current proper distance to the farthest regions whose light has reached us is about 46 billion light-years. That sphere defines the observable universe, but the cosmic horizon is a more general concept. It is any boundary set by the causal structure of space-time that restricts observation and communication. Different horizons arise depending on whether we ask how far back we can see, how far into the future we can send or receive signals, or what regions will forever remain beyond reach. The most familiar of these is the particle horizon. It is defined by the maximum comoving distance from which light could have reached an observer since the beginning of cosmic time. The particle horizon delineates the volume of the universe that has ever been in causal contact with us. Everything outside that limit may exist, but no information from it could possibly have reached us yet. In practice, the cosmic microwave background represents the closest observational trace of this horizon, because before the universe became transparent, photons could not travel freely. Thus, the particle horizon provides the outermost shell of what we can study directly with electromagnetic radiation. Closely related but conceptually distinct is the event horizon. While the particle horizon describes the past, the event horizon describes the future. It is the boundary separating regions from which light emitted now can and cannot ever reach us, no matter how long we wait. Because cosmic expansion is accelerating under the influence of dark energy, an event horizon exists for our universe. Galaxies that are now receding beyond a certain distance will eventually emit light that will never reach us, even if the universe lasts forever. This horizon is not located at the same distance as the particle horizon, and unlike the observable limit, it represents a permanent barrier to future communication. These horizons are not speculative. They follow directly from the solutions of general relativity applied to a homogeneous and isotropic universe. Calculating them requires integrating the history of expansion encoded in the scale factor and influenced by the densities of matter, radiation, and dark energy. While the mathematics may be intricate, the conceptual message is simple. Space-time expansion coupled with finite signal speed imposes strict causal limits. There's a sphere that contains all we will ever know through direct evidence, and beyond it lies the unreachable. Horizon concepts also highlight the difference between the Hubble radius and true causal boundaries. The Hubble radius, defined by the distance at which recession velocity equals the speed of light, is not a horizon in the strict sense. Galaxies can cross this radius and still send us light because photons can move inward even as expansion carries galaxies outward. Confusing the Hubble radius with a causal horizon has led to misconceptions, but the distinction is clear. The Hubble radius is an instantaneous measure of expansion, while horizons describe the long-term causal structure of space-time. The cosmic horizon is not fixed, it evolves with time. In the early universe, horizons were much smaller, and regions of space that today are far apart were once close enough to interact. This fact lies at the heart of the so-called horizon problem, one of the puzzles that motivated the theory of inflation. Observations show that the cosmic microwave background is remarkably uniform in temperature across the entire sky, even in regions that, under simple expansion, should never have been in contact. Inflation solves this by proposing a period of exponential expansion in the first fraction of a second, stretching a once small, causally connected patch to encompass the entire observable universe. In doing so, it explains why regions that appear causally disconnected today share the same initial conditions. In addition to electromagnetic signals, the cosmic horizon applies to other messengers. Neutrinos decoupled from matter much earlier than photons, so a cosmic neutrino background should exist with information from about 1 second after the Big Bang. Gravitational waves, which interact even more weakly, can travel freely from the earliest instants, potentially carrying information from times far closer to the origin than any other probe. If we one day detect this primordial gravitational wave background, our horizon for direct observation of the early universe will shift inward. Yet even then, a horizon will remain, because no finite speed signal can reach us from beyond certain limits defined by the geometry of space-time. The notion of a cosmic horizon also shapes our expectations for the fate of the universe. If dark energy continues to drive acceleration, the event horizon will become an unyielding barrier. Over billions of years, more and more galaxies will slip across it, vanishing from our future sky. Their light will redshift to invisibility, and the observable universe will shrink in content even as it grows in size. In the far future, only the nearest group of galaxies gravitationally bound to our own will remain visible. To hypothetical astronomers living in that future, the cosmic horizon will give the illusion of a small, lonely universe, erasing evidence of the grand structures we see today. The horizon thus has both an empirical and a philosophical role. Empirically, it defines the limits of cosmology as an observational science. We cannot design an experiment to reach beyond it, no matter how advanced our technology. Philosophically, it reminds us that knowledge is shaped by position and time. Another observer in a distant galaxy has their own horizon, overlapping but not identical to ours. They see galaxies invisible to us, just as we see galaxies invisible to them. No one perspective encompasses the whole. This relativity of horizons does not mean the universe is subjective, but it does mean that access to its contents is always bounded. In practice, astronomers must always work within this boundary. Surveys of galaxies, measurements of cosmic background radiation, and detections of distant supernova all take place inside our horizon. The fact that we can map billions of light years in every direction is extraordinary, but we remain inside a finite bubble of information. Every conclusion we draw about the global structure of the universe, such as whether it is infinite or finite, relies on extrapolation from within that bubble. The cosmic horizon ensures that a measure of uncertainty will always accompany our cosmological models. The concept of horizons extends beyond cosmology. Black holes possess event horizons that define regions from which nothing can escape. Uniformly accelerated observers perceive Rindler horizons, beyond which they cannot receive signals. These analogies help us understand that horizons are not exotic add-ons to relativity, but inherent features of causal structure. In every case, they separate what can influence from what cannot. In cosmology, the cosmic horizon is simply the largest and most fundamental of these. The existence of a cosmic horizon can feel unsettling. It tells us that the universe is larger than we can ever observe, that there are regions whose light will never arrive, and whose history will never touch ours. Yet it also provides a framework for humility and wonder. We are not at the center of the universe, but we are at the center of our observable horizon, just as every observer is. The symmetry of this arrangement affirms that our vantage point is not special, but it is still uniquely ours. Cosmologists continue to refine measurements of the horizon. Improved observations of the microwave background, galaxy clustering, and the behavior of distant supernovae sharpen estimates of the universe's expansion history, and therefore the size of the horizons. These refinements matter not only for abstract theory but also for practical understanding of the universe's evolution, the formation of structure, and the ultimate destiny of the cosmos. The cosmic horizon is, in the end, both a boundary and an invitation. It marks the outer edge of empirical science, the line beyond which evidence will never come. But it also challenges us to build theories that reach further, constrained by logic and tested within our horizon, but daring enough to imagine what lies beyond. In that way, the horizon is not the end of inquiry, but its engine, forever reminding us that the cosmos is larger than we know. And if we pause to reflect, we may find something quietly human in this cosmic fact. To live within a horizon is to live with limits, but also to live with possibility. Every photon we detect has crossed billions of years to reach us, carrying with it a fragment of the universe's story. Beyond the horizon, the story continues, unseen but not absent. The edge of observation is not the edge of reality. It is the place where knowledge meets mystery, and where imagination begins. Chapter 5. Beyond What We See, the Infinite versus the Finite. The universe we can observe fills a sphere about 46 billion light-years in radius, but that sphere is not a container and it is not the whole. Beyond the horizon, space continues. How far, in what shape, and with what global properties are questions that cannot be answered by looking alone. The sharpest version is simple to state and hard to settle. Is the universe infinite, or is it finite yet without edges? The answer matters because it reframes what we think space is, what typical means in cosmology, and how we reason about chance, causality, and information on the grandest scales. An infinite universe is one whose spatial slices, at a given cosmic time, extend without limit. There is no largest distance, no boundary to reach, no place where space ends. If matter is statistically homogeneous and isotropic, then on sufficiently large scales, the same kinds of structures recur, even though the specific pattern is always different. Taken strictly, infinity has a startling implication. With only a finite number of local arrangements permitted by physics in any bounded region, those arrangements must recur somewhere, not once, but endlessly. In an infinite cosmos, the observable universe would be a tiny patch of a boundless expanse, and improbabilities are softened because everything that is not forbidden eventually appears. A finite universe, by contrast, need not possess an edge. Space can be finite in volume, yet unbounded if it closes on itself. The familiar analogy is Earth's surface, finite area, no rim. In 3 dimensions, there is a rich menagerie of compact manifolds with no boundary, from the simple 3 torus obtained by identifying opposite faces of a cube to more intricate spherical and hyperbolic spaces. In such a cosmos, a traveler who moved long enough in one direction would return to the starting point, although the required path length could be so large that no physical journey could achieve it. Finite but unbounded means there is no outer wall to hit. It does not mean small. Geometry offers the first empirical leverage. In homogeneous and isotropic models, the sign of spatial curvature is linked to the ratio between the mean energy density and a critical density set by the expansion rate. If that ratio equals 1, spatial sections are flat. Above 1, they are positively curved. Below 1, they are negatively curved. Measurements of the cosmic microwave background, baryon acoustic oscillations in the galaxy distribution and wide-field galaxy clustering consistently indicate that on the largest scales we can probe, the spatial curvature is very close to zero. This does not prove infinity. A space can be so large and so nearly flat that no curvature is detectable within our horizon, yet still be globally finite. But the data do tell us that if space is finite, its characteristic scale must be far larger than the diameter of the observable universe. Topology addresses a different question, global connectedness rather than local curvature. A space can be locally indistinguishable from Euclidean 3 space and still be finite if the large-scale identifications wrap space back on itself. In a multiply-connected universe, light can take different routes to the same destination, potentially producing repeated images of distant structures in different directions and at different redshifts. A particularly clear signature would be matched circles. In the microwave background, pairs of circular patterns with identical temperature and polarization fluctuations arising from the same physical region viewed along different geodesics. So far, no convincing topological signature has emerged. Precision microwave background maps have not revealed robust matched circles once foregrounds, instrument noise, and scanning systematics are accounted for. Likewise, deep redshift surveys have not identified indisputable ghost images of the same galaxy cluster at multiple positions on the sky. These null results do not rule out finitude. They push the minimum wraparound scale outward. If space is compact, the shortest closed path must be larger than roughly the diameter of the last scattering surface, and plausibly much larger. In practice, this means that if the universe is finite, its closure likely occurs on scales so vast that the observable patch gives no direct hint of it. Inflation, the hypothesized episode of accelerated expansion in the first instance of cosmic history, supplies a theoretical reason to expect an extremely large, perhaps effectively infinite cosmos. During inflation, a tiny, causally connected patch can be stretched by an enormous factor, flattening curvature and diluting pre-existing irregularities. Our entire observable region would then occupy a minuscule piece of a vastly larger domain. In many models, inflation is not a single global event, but a process that continues in some regions while ending in others, spawning a mosaic of pocket universes embedded in an inflating background. Some of those pockets may themselves be spatially infinite. Others may be finite but huge. Collectively, they render the notion of the size of the universe more subtle than a single number. Yet infinity is not a concept physics embraces lightly. If space is infinite and structure formation and quantum fluctuations proceed without bound, then everything that can occur consistent with the laws of physics occurs somewhere, and it occurs infinitely many times. That raises the measure problem. How to assign probabilities when every allowed outcome happens an infinite number of times? Different ways of cutting off or ordering an infinite ensemble give different weights to different classes of events, leading to incompatible predictions for what a typical observer should see. The difficulty is not merely philosophical. Without a principled measure, statements about likelihood lose operational meaning, and paradoxes such as the dominance of freak Boltzmann brain observers over ordinary observers can arise in some models unless carefully controlled. A finite universe sidesteps part of that tangle. If the total volume is finite and the number of independent degrees of freedom within a causal patch is bounded, observers formed by ordinary astrophysical processes may overwhelmingly outnumber observers arising from rare thermal or quantum fluctuations. Probabilities can then be defined by counting within a single compact space or within a finite causal diamond over finite time, avoiding some of the ambiguities that plague infinite ensembles. But finiteness brings its own puzzles. What fixes the global size and topology? Why should space close on itself in one way rather than another? If the compactification scale is astronomically large, what physical principle chooses it? Observations continue to sharpen the picture at the scales we can probe. Baryon acoustic oscillations imprint a characteristic comoving scale in the galaxy distribution, furnishing a standard ruler that, combined with supernova distances and the microwave background, tightly constrains geometry. Weak gravitational lensing maps the growth of structure in a way sensitive to both geometry and expansion history, providing cross-checks independent of distance indicators. Together, these methods favor near-flat spatial slices across a wide range of redshifts. As constraints tighten, the window for significant curvature or for small compactification radii narrows, but a truly global verdict remains out of reach because our observations are confined to one horizon volume. Spatial scale must also be distinguished from temporal duration. A universe can be spatially infinite at each moment, and yet have a finite past, as many inflationary spacetimes appear to be geodesically incomplete to the past under broad conditions. Conversely, a spatially finite universe can expand indefinitely into the future. The hot Big Bang model describes an early hot phase followed by cooling and structure formation. By itself, it does not prescribe the global size or topology of space. Likewise, today's accelerated expansion, likely driven by dark energy with properties close to a cosmological constant, determines the behavior of horizons in the far future, but does not, by itself, decide between finitude and infinity. If the universe is finite and multiply connected, topology can influence physics even when direct repetitions are unobservable. Quantum fields in compact spaces satisfy boundary conditions that can shift vacuum energies and subtly alter fluctuation spectra at the largest angles. Some specific compact manifolds suppress correlations on very large angular scales, an effect that has been discussed in connection with the low-power anomalies of the largest-scale microwave background multipoles. Those anomalies might be statistical flukes, the natural outcome of observing only one sky, or the result of foreground residuals and systematics. Still, the possibility that topology leaves a faint imprint encourages continued scrutiny of the largest scales with better polarization data, where systematics differ from those in temperature maps. The finite versus infinite question also touches the way we think about information in cosmology. The late-time universe seems to approach a de Sitter-like phase with a cosmological horizon. By analogy with black holes, horizons carry entropies proportional to their areas in fundamental units, suggesting that the number of independent degrees of freedom, accessible within a single causal patch, may be finite. Some researchers interpret this as a hint that physics inside a cosmological horizon might be effectively described by a finite-dimensional Hilbert space, even if space outside the patch continues forever. Others view the horizon entropy as a thermodynamic property compatible with an underlying infinite description. Either way, the association between horizons and finite information content complicates a naive identification of infinite space with infinite observables. There remain concrete signatures worth watching. If space wraps around itself with a compactification scale only modestly larger than the diameter of the last scattering surface, matched circles with correlated temperature and polarization should appear in microwave background maps. If the wraparound scale is larger, repeated galaxy images could still occur in principle, although galaxy evolution, dust, and gravitational lensing complicate identification over cosmic time. A compact topology might also induce slight anisotropies in the distribution of the largest voids and superclusters, or leave subtle fingerprints in the cross-correlations between microwave background features and large-scale structure. Each of these effects is delicate, but together they create a portfolio of tests that will improve as surveys grow. Because we see only one sky and one Hubble volume, cosmic variance imposes a hard limit on what we can learn about global properties. Even with perfect instruments, there are only so many independent large-scale modes within our horizon, and the statistical uncertainties associated with those modes cannot be reduced by better technology. This is why some questions tied to global structure may remain permanently probabilistic. A model predicting features incompatible with what we see can be rejected, but a family of models that differ only beyond our horizon may never be distinguished empirically. That is not a failure of method. It is a fact about what finite signal speed and finite age imply. The stakes of the question extend beyond technique. In an infinite universe, the Copernican principle, we are not special, takes an extreme form. Our location is one of uncountably many. Our history, however intricate, is one thread among an unbounded weave. Typicality must be defined with care, and coincidences can no longer be dismissed as one-off quirks when every coincidence happens somewhere. In a finite universe, especially one not inconceivably larger than our horizon, the specific arrangement of structures we see may carry more explanatory weight, and questions about global initial conditions loom larger. In both pictures, humility is compulsory, but the flavor of that humility differs. The way forward is twofold. Observationally, we widen and deepen our maps. High-sensitivity microwave polarization will sharpen searches for matched circles and large-angle anomalies. Optical and near-infrared galaxy surveys covering vast solid angles will map structure to higher redshift and over larger comoving volumes. Weak lensing tomography will slice the mass distribution by distance, complementing clustering measurements with geometry-sensitive shear. 21-centimeter intensity mapping will trace neutral hydrogen through the cosmic dawn and reionization, opening a new window on large-scale modes that are otherwise inaccessible. Each technique is sensitive in a different way to geometry and to possible wraparound effects, and together they can either reveal subtle signatures of finiteness or keep pushing the lower bound outward. Theoretically, we refine early universe models and confront their global implications. We ask whether inflation can begin on compact spaces without erasing the topology, whether certain topologies are dynamically preferred, and how measures in eternal inflation can be defined without paradox. We probe the connections between horizon entropy, holographic ideas, and the number of independent degrees of freedom inside a causal patch. We examine whether anomalies at the largest angular scales are telling us about physics beyond the simplest inflationary scenarios, or are reminders that a single realization of a random field will sometimes look odd. Progress here will not be a single decisive experiment, but a convergence of consistency checks, non-detections, and perhaps one or two decisive patterns. From a human vantage, the contrast between infinity and finitude has different emotional textures. Infinity suggests a boundless sea where every possible shore exists somewhere out of sight and where our harbor is neither privileged nor alone. Finitude suggests a completed world, a single totality with a describable size and shape in which every part belongs to one continuous whole. Both pictures are compatible with the evidence we possess. both are vastly larger than anything in daily life. Both tell us that what we can see is only a fragment of what there is. And if we allow a brief moment of reflection, perhaps the most honest posture is appreciation. Whether the universe is endless or complete, the piece within our reach contains all the clues needed to explain how space expanded and cooled, how stars and galaxies formed, and how structure emerged from tiny ripples in the early plasma. Our horizon hides much, but it does not diminish meaning. The unknown beyond it is not emptiness. It is a reminder that reality exceeds any one perspective, and that science and imagination meet at the edge of what light can bring. Chapter 6. The Shape of the Universe. The question of the universe's shape is both mathematical and physical, both abstract and deeply tied to the way reality is structured. When cosmologists talk about the shape of the universe, they mean the large-scale geometry and topology of space, how lines and surfaces behave when extended indefinitely, how volumes grow with distance, and whether the whole is open, closed, or flat. This concept is not about the arrangement of galaxies or the visible distribution of matter, but about the fabric of space itself, the geometric framework within which all cosmic structures exist. Geometry in this sense is not decorative. It dictates the rules of motion, the propagation of light, and the fate of the universe's expansion. It determines whether parallel lines meet or diverge, whether space wraps back on itself or stretches outward forever. To know the universe's shape is to answer one of the deepest questions about existence: whether space is infinite, finite, or something stranger still. The foundation of our understanding lies in Einstein's general theory of relativity, which describes how matter and energy curve space-time. On local scales, the mass of a planet or star bends space-time so that orbits and trajectories follow curved paths. On cosmic scales, the combined density of matter, radiation, and dark energy determines the overall curvature of the universe. This curvature is described by the Robertson-Walker metric, a mathematical framework that assumes homogeneity and isotropy, the principle that on large scales the universe looks the same in every direction and at every location. Within this framework, three broad geometric categories arise: positive curvature, negative curvature, and flatness. The universe with positive curvature is analogous to the surface of a sphere. Parallel lines that begin alongside each other eventually converge, and the total volume of space is finite, though without a boundary. If the cosmos had strong positive curvature, traveling far enough in one direction might eventually return an observer to their starting point. A universe with negative curvature resembles the geometry of a saddle. Parallel lines diverge, and volumes grow faster with distance than in Euclidean space. Such a universe is infinite and unbounded. A flat universe follows Euclidean geometry. Parallel lines remain parallel, and the familiar rules of geometry hold across cosmic scales. Flatness permits infinite extent, though it can also be compatible with finite but unbounded topologies if space loops back on itself. Observational cosmology seeks to determine which of these descriptions matches reality. The most powerful evidence comes from the cosmic microwave background radiation, the afterglow of the early universe released when matter and radiation decoupled nearly 14 billion years ago. The tiny fluctuations in this radiation, mapped with exquisite precision by satellites such as WMAP and Planck, act as rulers across the sky. Their angular scale is sensitive to the geometry of space, because light rays travel along curved paths. If the universe were strongly positively curved, fluctuations of a given size would appear larger on the sky. If negatively curved, they would appear smaller. The observed pattern matches almost perfectly with flat geometry to within a fraction of a percent. This near flatness is one of the most striking features of the universe. Within observational uncertainty, curvature is consistent with zero. This suggests either that the universe is truly infinite and flat, or that it is finite with a radius so large that curvature is undetectable within our horizon. Inflationary cosmology provides an explanation. During inflation, a period of exponential expansion in the early universe, any initial curvature would have been stretched to near flatness, much as the surface of a balloon appears flat to an ant on a tiny patch. Inflation does not require the universe to be infinite, but it makes any detectable curvature unlikely. Yet shape is not defined by geometry alone. Topology, the global connectedness of space, adds complexity. Even if the universe is flat locally, it could have a finite multiply-connected topology. Imagine identifying opposite faces of a cube so that traveling through one side brings you back from the other. Such a three-torus would be finite but edgeless. More elaborate topologies are possible in 3 dimensions, including spaces with twists, reflections, and non-trivial connections. Each topology would imprint subtle patterns on the cosmic microwave background and on the distribution of galaxies, such as repeated circles or matched structures. Despite decades of searching, no clear evidence of such signatures has been found. This absence pushes any compact topology to scales larger than the observable universe. The search for the universe's shape also draws on large-scale surveys of galaxies and clusters. The distribution of matter on scales of hundreds of millions of light-years provides complementary constraints to the microwave background. Baryon acoustic oscillations, imprints of sound waves from the early universe, frozen into galaxy clustering, serve as standard rulers that test spatial curvature. These measurements confirm the flatness indicated by the microwave background with ever-increasing precision. Weak gravitational lensing, the subtle distortion of galaxy shapes by intervening matter, adds further information about geometry. Together, these tools paint a consistent picture. The observable universe is remarkably flat, homogeneous, and isotropic. Still, uncertainties remain. Even the most precise measurements cannot rule out curvature smaller than about 1 part in 1,000. This leaves room for possibilities. The universe could be truly infinite, stretching endlessly without curvature. Or it could be a gigantic closed sphere, so vast that within our horizon it looks flat. The distinction matters profoundly, but may remain beyond our capacity to measure directly. The shape of the universe is not only about size and curvature, but also about destiny. In classical cosmology, without dark energy, a positively curved universe would eventually halt its expansion and recollapse, while a flat or negatively curved universe would expand forever. The discovery of cosmic acceleration, driven by dark energy, changes this picture. Now, regardless of curvature, the long-term fate depends on the properties of dark energy. If it behaves like a cosmological constant, expansion will continue to accelerate, pushing galaxies beyond each other's horizons. If it evolves with time, stranger fates are possible, from slow fading expansion to catastrophic rip-apart scenarios. Geometry no longer dictates destiny, but it still frames the stage. Quantum cosmology adds another layer of speculation. Some models suggest that the universe could have arisen from a quantum fluctuation of a compact finite state, while others favor infinite open configurations. Theories of quantum gravity, still under development, may eventually reveal whether space has a discrete structure that enforces finiteness, or whether continuum models of infinity are valid descriptions. The holographic principle, inspired by black hole thermodynamics, even suggests that information within a volume may be encoded on its boundary, hinting at an entirely different way of conceiving shape and size. From a philosophical standpoint, the shape of the universe challenges our intuition. Infinity is a hard concept for the human mind, which evolved to navigate finite landscapes. The universe without end feels alien, yet so does a universe that closes on itself. The notion that space could loop back, making straight lines into circles on scales larger than the horizon, forces us to rethink what distance and direction mean. The idea that parallel lines might one day converge or diverge over cosmic scales shows how geometry shapes not just mathematics, but our vision of reality itself. Every improvement in measurement refines our knowledge of the universe's shape, but also deepens the mystery. As constraints on curvature tighten, the likelihood grows that we live in a cosmos so close to flat that for all practical purposes it is indistinguishable from infinity. Yet whether space is truly infinite or merely very large remains undecidable. No experiment can map beyond our horizon, and no signal can return from the unobservable. We are left to infer, model, and speculate, guided by evidence but bounded by causality. The shape of the universe is thus a reminder of both the power and the limits of science. With telescopes and mathematics, we have traced the geometry of space across billions of light years. We can say with confidence that the observable cosmos is nearly flat, homogeneous, and isotropic. We can describe the possible topologies and explore their implications. But the ultimate global shape, the full answer to whether the universe is infinite or finite, may never be accessible. And perhaps that is fitting. The universe does not owe us a simple answer. Its shape is written into the structure of space-time, not into our intuition. Whether infinite or finite, flat or curved, the cosmos is larger and stranger than human imagination evolved to grasp. The horizon of knowledge will expand, but the final truth may remain beyond reach. For a brief moment of reflection, one might see in this not defeat, but wonder. To live in a universe whose shape stretches beyond our knowing is to live in a reality that invites endless curiosity. Whether space is boundless or closed, its form is the stage upon which galaxies evolve, stars shine, and life emerges to ask these questions. The geometry of the universe is not only mathematics, it is the quiet backdrop of existence itself. Chapter 7. The Multiverse Hypothesis, Edges as Gateways. The word universe once meant everything, an all-encompassing totality. To speak of multiple universes would have sounded contradictory. Yet in modern cosmology and physics, the idea of a multiverse arises naturally from several independent lines of reasoning. It is not an idle speculation, but a framework that tries to extend the laws of physics beyond the boundaries imposed by our observable region. In this sense, the notion of edges as gateways captures the spirit. The limits of what we can see may not be the end, but rather the threshold into other domains, perhaps similar to ours, perhaps radically different. One of the strongest motivations for the multiverse comes from inflationary cosmology. Inflation proposes that in the first instant of the universe's history, a tiny patch of space underwent exponential expansion, growing by an enormous factor in a fraction of a second. Inflation explains why the universe is so uniform on large scales, why its geometry is nearly flat, and why small fluctuations seeded galaxies and clusters. But many inflationary models predict that inflation does not stop everywhere at once. Instead, it ends in some regions while continuing in others, a process known as eternal inflation. The result is a vast, possibly infinite space-time where bubble universes form in different places. Our observable universe would then be just one bubble among many. Each bubble in eternal inflation might have different physical conditions. Some may resemble ours, with stars, galaxies, and chemistry. Others may have different values of fundamental constants, different numbers of dimensions, or even different laws of physics. The landscape of possibilities arises from the way inflation is tied to quantum fields, which can settle into different configurations in different regions. In this view, the apparent fine-tuning of our universe, for example, the precise value of the cosmological constant that allows galaxies to form, might be explained anthropically. We find ourselves in a bubble with conditions compatible with life, because only such bubbles can host observers at all. Another route to the multiverse comes from string theory. As a candidate for a quantum theory of gravity, string theory requires extra dimensions beyond the familiar 3 of space and 1 of time. These dimensions can be compactified in many different ways, each giving rise to different low-energy physics. The number of possible configurations is staggeringly large, often described as a landscape of vacua. If different regions of the cosmos realize different compactifications, the result is again a multiverse, countless domains with varying laws of nature, all consistent with the overarching theory. Quantum mechanics itself hints at multiplicity. In the many worlds interpretation, every quantum event branches into different outcomes, each realized in a separate branch of the wave function. Though this version of the multiverse is conceptually different from cosmological bubbles, it shares the idea that our experience is only one thread among many possible realities. The boundaries we encounter are not absolute limits, but branching points where other versions of events unfold beyond our observation. The idea of a multiverse also helps address puzzles that otherwise appear unnatural. Why do the constants of physics take the values they do? Why does the cosmological constant have a value so small yet non-zero, balancing the expansion of space in a way that permits structure to form? In a single universe picture, such values may seem implausible coincidences. In a multiverse, they are simply local facts, one draw from an ensemble of possibilities. The anthropic principle, controversial but unavoidable in this context, then says we observe these values because only they allow the emergence of life and consciousness capable of observing. Despite its motivations, the multiverse is contentious because it challenges the traditional criteria of science. If other universes are forever beyond our horizon, can the hypothesis be tested? Critics argue that unobservable domains are metaphysical rather than scientific. Proponents respond that while we cannot observe other universes directly, we can test the theories that predict them. Inflation, string theory, and quantum mechanics are judged by their consistency with observations in our universe. And if those theories inevitably predict a multiverse, then the multiverse is an implication we must accept. Some suggest that indirect evidence might one day appear. For instance, if our bubble universe had collided with another in the past, leaving faint imprints on the cosmic microwave background. Searches for such signatures are ongoing, though no conclusive evidence has been found. Philosophically, the multiverse forces us to reconsider what the universe means. If our cosmic horizon is just one bubble among many, then edges are not boundaries of existence but gateways into broader reality. The observable universe becomes analogous to a local neighborhood, and the true cosmos is a vast collection of neighborhoods, each self-contained, yet part of a greater whole. This shift mirrors earlier moments in science when horizons expanded, from Earth to the solar system, from the solar system to the galaxy, and from the galaxy to the observable universe. Each time, what once seemed like the totality became just a part. The multiverse extends this pattern further still. Eternal inflation also raises questions about probability and measure. In a space-time where inflation never ends globally, there are infinitely many bubble universes. Anything not forbidden by physics occurs infinitely many times. How then can we make predictions? Assigning probabilities in an infinite ensemble is tricky because the result depends on how one defines the cutoff or ordering. This measure problem is a major unsolved issue in multiverse cosmology. Some approaches attempt to define probabilities by counting events within a finite causal diamond. Others appeal to holographic principles. None yet commands consensus. The idea of edges as gateways is striking here. Our cosmic horizon, usually seen as a limit, could be reinterpreted as a boundary beyond which other regions exist, inaccessible but real. In an eternal multiverse, every horizon is local, and beyond each lies a different patch of reality. Our bubble may expand forever, but it is only one blossom in an endless field. The edge of observation is not the end of existence, but the boundary of our domain. It is worth noting that the multiverse is not a single theory, but a family of scenarios. Cosmological inflation suggests one type, string theory another, and quantum mechanics yet another. These scenarios differ in detail but converge on the idea that reality is larger than our observable slice. Some cosmologists treat the multiverse as a plausible implication of known physics. Others view it as speculative. The debate is not only about evidence but also about the philosophy of science. Should unobservable entities count as part of physical theory? The history of physics suggests that sometimes they must. Atoms, quarks, and black holes were once unobservable, accepted because they were necessary parts of successful theories. The same logic might apply to the multiverse. From a practical standpoint, multiverse ideas have inspired searches for observational footprints. If another bubble had collided with ours during inflation, it might have left circular patterns or anisotropies in the microwave background. If string theory's landscape is real, then statistical distributions of constants might be inferred. None of these searches has yet borne fruit, but the absence of evidence does not yet count as evidence of absence, given the subtlety of the signals and the difficulty of separating them from noise. For human thought, the multiverse is both exhilarating and unsettling. An infinite ensemble of universes dilutes the uniqueness of our own. If every possible version of reality exists somewhere, then our particular history may feel less special. But it also emphasizes the extraordinary fact that in at least one universe, conditions aligned so that life arose and consciousness wondered about its place. In a multiverse, our existence is not impossible, but inevitable somewhere, and we happen to be in one of the rare places where it occurred. Even if the multiverse is ultimately unprovable, grappling with it enriches cosmology. It clarifies what our theories imply, what counts as an explanation, and how far reasoning can extend beyond observation. Whether or not we ever confirm the existence of other universes, the multiverse hypothesis serves as a conceptual gateway, opening our imagination to the possibility that reality is far greater than the bubble we see. And if we pause for a moment of quiet reflection, we might feel the weight of the thought that what seems to be everything may be only a fragment, that the edge of vision may not be an end, but a passage. To live in such a cosmos is to accept that mystery is not beyond us, but around us, woven into every horizon. Whether the multiverse exists or not, The very fact that our physics points toward it reminds us that reality is richer than we ever expected. Chapter 8. Cosmic Darkness, What Lies Beyond Our Horizon. When we look into the night sky, even with the most sophisticated observatories, we are taking in only a small slice of reality. The sphere we call the observable universe has a present-day radius of roughly 46 billion light-years. That limit is not a wall made of matter. It is a boundary set by time and causality. The universe has a finite age, light travels at a finite speed, and while ancient photons were en route, the fabric of space itself expanded and stretched the paths they had to cross. Beyond the edge of what we can see lies a region we cannot reach by any signal sent now or in the future. That unseen region is not an absence, it is cosmic darkness, the continuation of reality beyond our horizon. The most cautious expectation for what inhabits that darkness is continuity. Within our horizon, the cosmos looks statistically homogeneous and isotropic on very large scales. When galaxy positions are averaged over hundreds of millions of light-years, clumps and filaments give way to uniformity. The cosmic microwave background, after careful removal of foreground emission, shows nearly the same temperature in every direction, with tiny fluctuations that follow simple, nearly Gaussian statistics. These observations suggest that the physical laws and broad patterns that hold across our visible sky persist beyond it. If that is true, then the darkness beyond is filled with more of the same cosmic web. Long filaments of dark matter and gas, clusters bound by gravity, and voids that span tens of millions of light-years, all evolving under identical rules. Continuity, however, does not mean perfect identity. Inflationary cosmology, which explains the near flatness and uniformity of the visible universe, predicts quantum fluctuations in the early expansion that were stretched over a wide range of scales. Some of those modes are longer than the diameter of our observable region. We experience only a small part of such a wave, like an ant walking across a gentle swell on the sea. The effect would not be to change the laws of physics from one place to another, but to nudge the mean density or curvature over distances far larger than we can survey. If such superhorizon modes exist, then our patch is a locally representative sample of a larger pattern we cannot fully see. There is a more radical possibility. In many models, inflation does not end everywhere at once. It ceases locally while continuing elsewhere, producing a patchwork of domains often called bubbles. Each domain cools into a vacuum state with its own low-energy parameters. Our horizon would then enclose one such domain. Beyond it, there could be other domains where particle masses, interaction strengths, or even effective dimensionality differ. The distances between domains would be so great, and the barriers between vacua so formidable, that no exchange of influence could occur. If this picture is right, the darkness beyond is not simply more of our familiar cosmos, but a mosaic whose tiles never overlap in causal contact. Even without invoking distinct domains, the unseen could hold specific structures that matter for what we do observe. There might be very large superclusters or supervoids beyond our horizon whose gravity tugs on matter at the limit of our surveys. We would never see those structures directly, but their presence could produce coherence in the peculiar velocities of galaxy clusters near the edge of our map. The late integrated Sachs-Wolf effect offers another pathway. As the universe accelerates, the gravitational potentials associated with very large structures decay with time. Microwave background photons crossing those evolving potentials receive tiny energy shifts. An unusual arrangement of mass outside our horizon could, in principle, leave a faint correlated imprint across the largest scales of our sky. Modern cosmology is developing tools designed to push inference right up to the horizon. Gravitational lensing of the microwave background measures the minute deflections imprinted by all the intervening mass between us and the last scattering surface. Unlike galaxy surveys, which fade with distance as galaxies become too dim and too few to resolve, lensing integrates the effect of structure along the entire line of sight, making it naturally sensitive to matter almost all the way to the horizon. Maps of the lensing deflection field are already revealing the growth of structure with time, and future surveys will sharpen those maps to test whether the largest scale statistics match the assumptions of homogeneity and isotropy. Low-frequency radio astronomy offers a complementary path. Neutral hydrogen emits radiation at a wavelength of 21 centimeters. And by measuring that line in aggregate across wide areas and a range of frequencies, line intensity mapping can build three-dimensional pictures of the intergalactic medium during cosmic dawn and reionization. These maps reach back to times when the first stars ignited and the earliest black holes began to heat their surroundings. Because intensity mapping does not require identifying individual galaxies, it can probe immense volumes efficiently, testing whether the distribution of matter and radiation is statistically the same in every direction as we approach the edge of what light allows. The time domain adds yet another window. The Sand Age Lobe Redshift Drift experiment proposes to monitor tiny changes in cosmological redshifts over decades. The expected signal is minute, but in principle, it traces the expansion history directly, independent of the standard candles and rulers that currently anchor our measurements. A detection would provide a clean check on how quickly the event horizon grows, and thus on how rapidly regions pass irreversibly into future darkness. Standard sirens, gravitational wave measurements of merging compact objects with identified host galaxies, offer an independent distance scale. As those measurements accumulate at higher redshift, they will help verify whether the expansion history remains consistent across the deepest parts of our light cone. Other messengers carry their own reach and their own limitations. Ultra-high energy cosmic rays collide with photons of the microwave background and lose energy, which restricts how far they can travel before arriving at Earth. Very high-energy gamma rays are attenuated by the extragalactic background light, making the distant universe opaque at those energies. Neutrinos and gravitational waves travel far more freely, but bright sources are rare, and detectors are only now reaching the necessary sensitivity. Each channel therefore has an effective horizon set by interactions, source populations, and instrument capabilities. None of these horizons aligns with the cosmological one, but taken together, they help triangulate the distribution of matter and energy near the edge of visibility. Between galaxies lies a reservoir of information about the unseen. Most ordinary matter in the universe resides not in stars, but as thinly spread gas tracing the cosmic web. As light from distant quasars passes through that gas, it accumulates a forest of absorption features that encode density, temperature, and composition over billions of years. With enough background sources, tomographic reconstructions can build genuine three-dimensional maps of the web at redshifts where galaxies are challenging to catalog. Because such maps are sensitive to the longest wavelengths in the density field, they are valuable probes of possible superhorizon modes that our patch of sky only samples incompletely. All sky backgrounds add further leverage. The net glow from faint, unresolved galaxies in the infrared and in radio bands carries information about the abundance and clustering of sources at high redshift. Measuring the dipole and higher multipoles of those backgrounds and comparing them with the expectations from our motion through the cosmic rest frame provides stringent tests of global consistency. If the observed dipoles do not align with a purely kinematic origin, then a large-scale intrinsic anisotropy could be present, suggestive of structure on scales so large that only a small piece lies within view. Topology offers a different connection to the unseen. If space loops back on itself on scales not absurdly larger than the last scattering surface, the sky would contain repeated patterns as light from the same structures arrived along different paths. The clearest signature would be matched circles in the microwave background, pairs of rings with identical temperature or polarization patterns. No robust detections have emerged, which pushes any such wraparound to very large scales and implies that if space is compact, the shortest closed path is well beyond our horizon. Even so, topology could still leave subtle statistical fingerprints on the largest modes, encouraging continued searches with cleaner polarization data. Thermodynamic ideas give cosmic darkness an informational face. In general relativity, horizons behave in ways that resemble ordinary thermodynamic systems. A cosmological event horizon can be associated with a temperature and an entropy proportional to its area in fundamental units. If that analogy is more than a metaphor, it suggests that the number of independent degrees of freedom accessible to any one observer is finite, even if space itself is unbounded. On that reading, darkness is not just spatial remoteness, it reflects an information bound. No matter how refined our instruments become, there is an upper limit to the distinct, observable facts available within a single causal patch. Practical cosmology must therefore thread the needle between ambition and humility. The assumptions of statistical homogeneity and ergodicity are not decorative. They are the pillars that allow us to use the sky we have as a fair sample of the universe we cannot see. We test those assumptions whenever we compare the statistics of disjoint sky patches, cross-correlate different observables, or search for position-dependent power. Thus far, the evidence points to a universe that is as simple on the largest scales as our models assume. Yet we also know that if our region were slightly atypical because of a superhorizon fluctuation, parameter inferences could shift subtly. Designing analyses that are robust to such possibilities is an active area of work. There is also a statistical floor that no instrument can cross. The largest angular scales on the sky contain only a few independent modes. We cannot create more of them by building bigger telescopes or integrating longer. This intrinsic limit is called cosmic variance. It means that some questions about the very largest scale pattern will never be answered with certainty. Debates about alignments of low-order multipoles, about hemispherical power asymmetries, or about a deficit of power on the largest scales live precisely in this regime where the data are sparse by the nature of the problem. The boundary with darkness is therefore not only causal, it is statistical. As the universe ages, cosmic darkness will change character. The microwave background will cool and redshift to wavelengths so long and with such small brightness that no finite technology could detect it. Galaxies not gravitationally bound to us will slip beyond the event horizon, their spectra stretched until they fade from view. The anchors that let us measure geometry and composition today will erode. In that remote era, astronomy will become parochial by necessity. The inhabitants of a far future galaxy group would see a small, seemingly isolated universe and might have few clues that their island once sat inside a vast web. To them, cosmic darkness will not lie only beyond the horizon. It will have swallowed almost everything we now study. Nothing in the argument for darkness implies that the unseen is arbitrary or lawless. The same equations that govern structure formation here apply there. Gravity draws matter together, photons redshift with expansion, and nuclear reactions build elements according to familiar pathways. Even if radically different domains exist somewhere in an inflationary multiverse, they are separated from us by distances and barriers that prevent any mixing. The edge of what we can know is therefore not a cliff where laws change abruptly, but a fog line beyond which details blur while the underlying grammar of nature carries on. Placed side by side, horizons, geometry, and expansion explain why cosmic darkness exists and how it evolves. The horizon is the causal boundary that marks what signals can reach us. Geometry dictates how lines, angles, and volumes behave as we sight toward that edge. Expansion, now accelerated by dark energy, determines whether the frontier between light and dark advances or retreats, and how quickly the inventory within it thins. Cosmic darkness is the honest name for the region assembled by these ingredients, real, structured, subject to the same rules, and yet permanently beyond our light cone. For a moment of reflection, it is worth noticing what has already been distilled from the thin trickle of information that does reach us. From a small planet around an ordinary star, we have mapped the afterglow of the first atoms, weighed the invisible matter that scaffolds galaxies, sensed the pressure of vacuum energy on the expansion, and traced the growth of structure across most of cosmic history. We have done this while confined to one sky and one vantage point, and while most of the universe remains out of reach. That success is both a triumph and a lesson. It shows that careful reasoning and measurement can extract profound truths from limited views, and it reminds us that limits do not make knowledge trivial. They make it precious. And if one final quiet thought can stand, let it be this: the cosmos does not end where our sight ends. The night is deep, and most of it will remain unlit to us. Yet, within the small sphere of light that reaches Earth, there is already enough grandeur to last as long as curiosity endures. Beyond that sphere, the universe continues, indifferent to our vantage and generous with its stories to any world where light and time can be gathered. The boundary between light and darkness is not a wall, but a moving shoreline, and standing on it is not a frustration. It is what makes the view sublime. Chapter 9. The Fate of the Edge. Will it change over time? The cosmic horizon, the ultimate limit of what we can see, is not fixed. It is not like a rigid boundary drawn on a map, but a moving frontier shaped by time, light, and the expansion of the universe. To understand whether the edge of the universe will change is to explore how horizons evolve, how cosmic expansion influences what is accessible to us, and how the future of the cosmos dictates what will eventually remain within sight. The fate of the edge is one of the most subtle and profound questions in cosmology, because it is tied directly to the destiny of space itself. When we speak of the cosmic edge, we mean the limits of observation and influence. The observable universe today spans about 46 billion light-years in radius, a result of light travel time and the stretching of space. This is not a static measure. It has grown since the birth of the cosmos. Early in the universe's history, the observable sphere was much smaller. As time passed, more light had the opportunity to reach us, and the horizon expanded. If the universe were to continue indefinitely without acceleration, our observable sphere would grow ever larger, bringing new regions into view. Over immense timescales, the edge would recede, revealing more and more of reality. Yet expansion is not simple. In the universe's youth, radiation dominated and expansion was rapid. Later, matter took over, and gravity slowed expansion, allowing more distant regions to come into sight. In the last few billion years, however, dark energy has begun to dominate, and the expansion is now accelerating. This change alters the fate of the edge profoundly. Instead of endlessly revealing more, the observable universe will eventually settle into a state where new regions stop entering our view. Many galaxies that we see today will slip away, their light stretched beyond detectability as they cross the event horizon. The difference between horizons must be emphasized. The particle horizon defines how far back we can see, determined by the age of the universe and the speed of light. The event horizon, by contrast, defines how far into the future signals emitted today can travel before expansion carries them away irretrievably. Our particle horizon has grown steadily and continues to expand as light from more distant regions arrives. But our event horizon sets a final limit on how far our influence can ever reach and how much of the universe will remain accessible. As cosmic acceleration proceeds, the event horizon becomes the decisive factor. Galaxies now at moderate redshift are still visible, but the light they emit in the future will never reach us. Over tens of billions of years, only galaxies gravitationally bound to our local group will remain visible. Beyond that, everything else will fade into the cosmic dark. The edge, then, will not continue to reveal more of the cosmos indefinitely. Instead, it will gradually erase parts of the sky, sealing them beyond reach. From a physical standpoint, this outcome depends on the nature of dark energy. If dark energy is truly a cosmological constant, unchanging vacuum energy, then accelerated expansion will continue forever, and the event horizon will remain fixed at a finite distance. In that scenario, the fate of the edge is sealed. After a finite time, all but the nearest structures will disappear beyond it. If, however, dark energy evolves, the picture could change. If its density diminishes over time, acceleration might slow, and the edge could once again expand to include more of the universe. If it grows stronger, the acceleration could become extreme, leading to scenarios like the Big Rip, where even local structures are torn apart. In that case, the edge would not merely hide distant galaxies, but would encroach inward, devouring everything. Cosmologists test these possibilities by measuring the expansion rate at different epochs. Supernova surveys, baryon acoustic oscillations, and the cosmic microwave background all contribute to reconstructing the expansion history. So far, the evidence points to dark energy being consistent with a cosmological constant. But uncertainties remain, and subtle deviations could alter the long-term fate of the horizon. Understanding the fate of the edge is therefore tied directly to one of the greatest mysteries in physics, the nature of dark energy. The far future of the edge also intersects with entropy and information. As regions vanish beyond the event horizon, the information they contain becomes inaccessible to us. In analogy with black hole horizons, a cosmological horizon can be assigned an entropy proportional to its area. That entropy represents the maximum amount of information that can be stored within our observable patch. As the edge stabilizes under acceleration, the information capacity of our causal domain becomes fixed. No matter how advanced future civilizations become, they will be confined to a finite reservoir of knowledge. In that sense, the fate of the edge is also the fate of information. On human timescales, the edge is not static either. The cosmic microwave background we observe today carries light released 380,000 years after the hot early phase. As time passes, that radiation redshifts further, cooling and dimming. In trillions of years, it will fade into wavelengths so long and faint that no conceivable detector could capture it. The ultimate record of the early universe will then be gone from view. Future astronomers may live in galaxies surrounded by empty darkness, with no trace of the grand expansion we infer today. To them, the edge will appear close, concealing the true immensity of the cosmos. Our perspective is unusual in this regard. We live in a cosmological era when the universe is old enough to reveal its large-scale structure, yet young enough that the evidence has not faded. We see galaxies receding but still in view, and we detect the microwave background as a faint but accessible glow. In the future, the edge will change in ways that erase these signs. The fate of the edge is not only a scientific question, but also a temporal one. It looks different depending on when one asks. This realization shapes how we think about cosmology itself. The edge is not fixed, but evolving. Today it expands, tomorrow it will contract in content, and eventually it will leave only a local island of matter surrounded by endless darkness. In that sense, our horizon is a temporary window, one that opens wide for a brief cosmic moment before closing again. To live now is to live at the fortunate time when the window is widest. For cosmologists, the fate of the edge underscores the urgency of observation. The sky today contains information that will not be available in the far future. Every map of galaxies, every measurement of cosmic background radiation, every detection of distant quasars and supernova is part of a record that will eventually vanish. Our descendants in distant eras will not have the same view. The universe will not end, but its edge will shift in ways that obscure its true scale. Some argue that this gives us a special responsibility. We are the generation that can measure the cosmos when it is most revealing. We can trace its structure across billions of light years, reconstruct its history from the first atoms to galaxies and stars, and glimpse the forces shaping its future. The fate of the edge means that this knowledge will not always be possible. Our cosmic moment is a privileged one where the edge offers its greatest breadth before closing down. And yet, even if horizons change, reality continues beyond them. Galaxies will persist beyond our view, structures will form and dissolve, stars will shine and die, and space will keep expanding. The edge is our limit, not the universe's. Its fate tells us not about the end of existence, but about the end of our access to existence. To ask about the fate of the edge is to confront the gap between reality and knowledge, a gap that widens as time goes on. If we pause to reflect quietly, this knowledge is sobering and beautiful. The edge of the universe is not fixed. It is alive with time. It grows, it shrinks, it changes with the balance of forces in the cosmos. To us, it is a horizon of possibility. To the universe, it is nothing at all. The fate of the edge is a story of limits, but also of wonder. A reminder that we live at a moment when the cosmos is open to us, and that what lies beyond the light will always invite imagination. Chapter 10. Standing at the Edge, Human Meaning in a Boundless Cosmos. To conclude a journey through horizons, geometry, and fate is to face a human question. What does it mean to live at the edge of what can be known? In modern cosmology, the edge is not a rim of matter, but a horizon set by the finite speed of light and the finite age of the universe. A boundary that shifts with cosmic time and with our position. It is also an epistemic line. Inside it, evidence can arrive. Beyond it, reality continues without ever becoming data for us. To stand at the edge is therefore to accept both the reach of knowledge and the reality of limits, and to work within that tension. Scientifically, standing at the edge means inhabiting a finite causal domain. The present-day radius of our observable sphere is about 46 billion light-years, because while photons were in flight, the fabric of space expanded, stretching the paths they took. Inside this sphere, independent lines of evidence interlock to form a coherent model. The spectrum and tiny anisotropies of the cosmic microwave background, the large-scale clustering of galaxies, the relative abundances of the light elements, the dynamics of clusters and rotation curves, strong and weak gravitational lensing, and the observed acceleration of expansion. The consilience of these facts is what gives cosmology its confidence. None of the ingredients alone would suffice. Together, they describe a universe that is nearly flat on large scales, dominated by dark matter and dark energy, and structured by the growth of tiny primordial fluctuations into the cosmic web. The horizon is a scientific boundary, but it is not an excuse for undisciplined speculation. Cosmology faces underdetermination in a principled sense. Distinct global models can agree on all observables within one Hubble volume. That is not a weakness of the field. It is a fact about causality. The way forward is not to insist on answers that cannot be obtained, but to refine the methods that decide among testable possibilities. We prefer models that fit diverse data with few adjustable parameters, that make predictions which survive independent checks, and that remain stable under reasonable changes in assumptions and analysis choices. Bayesian model comparison, cross-validation with orthogonal probes, blind analyses, and rigorous treatment of systematics are not bureaucratic hurdles. At the edge, they are the only routes to reliable knowledge. Our moment is unusual. The universe is old enough to have acquired rich structure, yet not so old that acceleration has erased the primary evidence. We can still detect the microwave background as a faint glow. We can still see galaxies near the reionization frontier. We can still triangulate geometry with supernovae, baryon acoustic oscillations, and weak lensing. This cosmic afternoon is temporary. In the far future, freely streaming backgrounds will redshift beyond detectability, and unbound galaxies will slip beyond our event horizon. Much of what makes cosmology possible today will fade. Recognizing this does not diminish our results. It clarifies their context. We occupy a brief era when the sky is unusually generous with information. The edge is also an informational object. General relativity and quantum field theory together suggest that horizons possess entropies and temperatures, and that a finite area sets a finite bound on accessible information. Whatever the ultimate microscopic interpretation, the practical message is clear. There is a limit not only to what can be seen at once, but to the number of distinct, non-redundant facts that any single world line can ever gather. That limit is not a failure of technology. It is part of the architecture of space-time. The finiteness of accessible information does not make inquiry trivial. It makes it precious, and it locates meaning in the careful allocation of attention. From that budget follows a concrete ethic for how we do science. If knowledge is to accumulate across centuries, data must survive not just as files, but as rerunnable analyses. Raw measurements should be preserved with calibration frames, reduction recipes, and software environments frozen in forms resilient to bit rot and shifting dependencies. Sky surveys need stewardship plans as serious as those for mirrors and cryostats. The metadata that lets a future analyst reprocess a spectrum or reweigh a catalog is part of the instrument as surely as the mirror, the cryostat, or the mount. What we are building, alongside telescopes, is an archive able to keep faith with future questions we cannot yet articulate. There is a planetary dimension to this ethic. The night sky is a commons. Light pollution, radio interference, and orbital debris are not abstractions. They are ways a species can dim its own window on the universe. Protecting radio quiet zones, coordinating satellite constellations to mitigate trails and reflections, designing deorbit plans that actually deorbit, and budgeting carbon for energy-intensive facilities are now part of doing astrophysics responsibly. Because the baseline for many experiments is the unpolluted sky, environmental choices are not orthogonal to discovery. They are the preconditions for it. The same edge teaches humility about inference at scale. Modern surveys deliver petabytes. Pipelines are necessarily complex. Machine learning helps classify, compress, and cluster these torrents, but pattern finding is not the same as understanding. Models that interpolate brilliantly can fail at extrapolation in subtle, cosmology-relevant ways. Simulation-based inference, forward modeling skies from a theory and comparing to data with realistic systematics, has become indispensable because it embeds the relevant physics and the nuisances together. The lesson is to join human judgment to computation, to prefer transparent models where possible, and to calibrate against truth-like simulations before trusting any conclusion drawn at the limit of precision. Meaning also flows from the long arc of discovery. For earlier generations, horizons meant coastlines, then the atmospheric limit, then the boundary of the solar system, then the extent of the Milky Way. Each time the edge receded, culture changed. Art absorbed new scales. Religion and philosophy reconsidered place and purpose. Social orders adjusted to the wider frame. Astronomy has repeatedly displaced us from imagined centers while enlarging solidarity by revealing kinship at the level of elements and starlight. The cosmic horizon continues this work. It enforces provincialism. Each observer is central only to their own bubble, while narrating a universal history we share. It is tempting to read existential futility into this picture. If most of reality will forever be beyond contact, why care? The scientific response is that the part within reach is already inexhaustible. The microwave background's microkelvin texture encodes the acoustics of a hot plasma. The galaxy distribution preserves the imprint of primordial sound waves. Black holes furnish laboratories for gravity under extreme curvature. Exoplanet atmospheres let us place Earth in context. The philosophical response is that meaning is made in right relation to truth, not granted by size. The cosmos does not give significance by volume. We make significance by the honesty and care with which we meet what is given. Education becomes the way attention propagates in time. To keep the edge bright, we need citizens who can reason across orders of magnitude, parse uncertainty and tolerate the difference between unknown and unknowable. Teaching cosmology as a living process, data to model to prediction to new data, builds that literacy. So does showing how dissent and debate work inside science, so that disagreement is seen not as failure, but as a mechanism for error correction. The point is not to mint astronomers, it is to cultivate habits of thought that can live with vast scales and honest uncertainty. There's also a dialogue between science and culture that the edge can deepen. Artists and writers have long metabolized astronomical discovery into new forms. Their metaphors, in turn, help scientists communicate without distortion. The language of fabric, web, and horizon are already such borrowings. Being explicit about their limits. Space is not literally cloth. A horizon is not a physical curtain. keeps imagination fertile without letting imagery calcify into misconception. Standing at the edge invites clarity without literalism, so that poetry and physics can illuminate rather than confuse. On the technical horizon, next-generation instruments will move the line of what we can infer, even if not the line of what we can see. Arrays on the lunar far side could map neutral hydrogen from the cosmic dark ages before the first stars. Cold mid-infrared observatories will inventory temperate terrestrial exoplanets and study their atmospheres for chemical disequilibria. Kilometer-scale gravitational wave detectors will chart mergers out to cosmological distances, building a distance ladder independent of light. Deep underground neutrino observatories will listen to core collapse supernovae across the nearby universe. None of these will dissolve the horizon, but each will let us read it with finer resolution. Intergenerational projects will be required, and that forces us to rehearse continuity. How do we build institutions that keep a mission coherent across decades? How do we design software that can be read when today's languages and libraries are historical curiosities? How do we choose data formats that are not long-term traps? These questions sound bureaucratic, but they are as fundamental to standing at the edge as any equation. The edge is patient. We must be too. Another form of patience concerns typicality and anthropic reasoning. Earlier chapters noted the hazards, measures on infinite ensembles, and selection effects that masquerade as explanations. A practical stance is modest. Use anthropic reasoning only when it is anchored to a candidate dynamics that also makes non-anthropic predictions we can test within our horizon. Avoid confusing necessary for us to exist with sufficient to explain why parameters have their values. Standing at the edge encourages explanations that earn their keep. The edge also reframes ethics inwardly. A planet that can host a lineage capable of measuring the universe is rare by any reasonable accounting. That rarity suggests obligations to reduce risks that could end the experiment prematurely, to support institutions that tell the truth about nature, to balance exploration with care for the only biosphere we know. Cosmology does not dictate policy, but it does sharpen stakes. The difference between a future with open skies and one where the heavens are a noisy billboard is not merely aesthetic, it is epistemic. None of this requires mythologizing science as the only source of meaning. Rather, it proposes a compact between disciplines. Let physics describe the constraints, the horizons, the curvatures, the fates. Let philosophy clarify what kinds of questions can be answered and how to live with those that cannot. Let the arts translate scale and limit into experience. At the edge, these are not rivals. They are lenses, each pulling a different frequency from the same spectrum of reality. In daily life, horizons shrink to the scale of rooms, screens, and schedules. Remembering the cosmic edge can reset proportions without inducing paralysis. A crisis matters no less because Andromeda is 2 million light-years away. A joy is not trivial because the Virgo cluster is 50 million light-years distant. What the edge offers is a way to hold urgency and perspective together, to act, knowing that action unfolds in a universe both indifferent and intelligible. The science will continue. Better measurements will tighten curvature bounds. Topology searches will probe larger wraparound scales. Redshift drift experiments may one day watch the expansion change directly. Simulations will grow in fidelity. Theory will explore quantum gravity's bearing on horizons and information. Each step will refine the shape of the edge. None will abolish it. That permanence is liberating. If the edge cannot be erased, our task is not to conquer it, but to attend to what lies inside it with care. One can formulate a simple, durable creed from all this. The universe is larger than we can see. The part we can see is enough to learn truth. Learning truth is a practice that depends on honesty, patience, and shared tools. And meaning is not a property the universe grants, but a pattern we make in right relation to what is real. Standing at the edge, that creed is not small. It is permission to proceed. And if we may allow just 2 quiet sentences for the heart. The horizon is not a wall, but a shoreline. We live where the light meets the dark, and the tide keeps coming in. My friend, we've traveled far tonight, all the way to the horizon of the universe itself. If you're still awake and want to keep floating through the cosmos, another video is waiting for you here. And if your eyes are already heavy, may your dreams be soft, and may they carry you gently among the stars. Sweet dreams.